So, as for introduction, forensic toxicology uses an analytical technique to identify drug evidence in criminal investigation. Drug abuse is a major issue affecting health and society. UV visible spectroscopy helps identify substances through absorbance characteristics and concentration of analysis. Scanning electron microscopy, also known as SEM, analyzes particle morphology and surface structure. This study uses UVVs and SEM to characterize selected drug samples for forensic analysis. As for objective, it is to identify physical and chemical characteristics of drug samples. Second, to determine the concentration using UVV spectroscopy. Third, to construct calibration curve for standard and unknown samples. Fourth, analyzes morphology using SEM. Fifth, to interpret forensic finding for drug identification.
The selected drug for this project are paracetamol and ibuprofen. Both are commonly used pharmaceutical drugs and are widely available as over-the-counter medications. Paracetamol is an analgesic and antipyretic drug used to relieve pain and reduce fever. It usually appears as a white crystalline powder and has the molecular formula C8H9NO2. Chemically, paracetamol contains hydroxyl and amide functional groups, which contributes to its UV absorption properties. Ibuprofen is a non-steroidal anti-inflammatory drug, or NSAID, used to reduce pain, inflammation, and fever. It also appears as a white crystalline solid and has the molecular formula C13H18O2. Ibuprofen contains a carboxylic acid group and an aromatic ring, making it suitable for UV spectroscopic analysis. Both drugs are relevant in forensic toxicology because overdose or misuse may cause serious health effects, including liver toxicity for paracetamol and kidney or gastrointestinal damage for ibuprofen. Next is SEM analysis method. Sample preparation as follows, which is ground sample using mortar and pestle, mounted powder on carbon adhesive tape, and then attached to aluminum SEM stop, and then excess powder removed carefully to produce a clearer microscopic image. For the SEM analysis, the system will be operated under high vacuum at around voltage 25 kV. Different magnification were used to observe surface morphology, crystal shape, particle size, and surface texture. For the data interpretation, the image of both drug sample particles will be compared. So from the SEM micrographs, differences in particle shape, crystal arrangement, and surface texture were identified. So these morphological characteristics can help support the identification of drug evidence in forensic analysis. For the image at 500 times magnifications, irregular particle shapes and ground surface morphology can be observed. So some particle agglomeration is also visible, showing that the particles are clustered together with different size distribution. The image at 1000 times magnifications, the crystal structure becomes clearer and more detailed. The particle appears pigmented with sharp edges and coarse surface texture. The higher magnification helps us study the morphology and particle characteristics more accurately. At 1000 times magnification, the ibuprofen particles show a more detailed surface structure. The particles appear flaky and rough with visible crystalline features. Smaller particles can also be seen attached to larger aggregates, confirming agglomeration and irregular morphology of the ibuprofen sample. The image at 1000 times magnifications, the crystal structure becomes clearer and more detailed. The particle appears pigmented with sharp edges and coarse surface texture. The higher magnification helps us study the morphology and particle characteristics more accurately.
Crush and accurately weight 100 mg of paracetamol pills using mortar and pestle. And then put the crushed pills inside the volumetric flask. Measure 70 ml of methanol and then adding up to calibrate mark of 100 ml in a volumetric flask to give a concentration of 1000 mg per liter or 1000 ppm. Repeat the same step for ibuprofen. The stock solution was serially diluted to prepare several working solutions with low concentration. Run the baseline and the scan range for both drugs are as such. Standard solution for both drug samples were prepared in different concentration. Pour the solution into the quartz cuvette. Put the sample inside the UV vis and press start to measure. Once done, save the curve and press data processing to identify the peak. Take out the previous sample and redo for the next sample.
Next, I will present the UVV spectroscopy analysis conducted for paracetamol and ibuprofen sample. UVV spectroscopy was used to identify the characteristic absorption peaks for both drugs and to determine the concentration of unknown sample quantitatively. The analysis was performed within the wavelength range of 200 to 400 nanometers. After scanning the sample, the characteristic absorption spectra were obtained for both drugs. For paracetamol, the maximum absorbance wavelength was observed at approximately 243 nanometers, meanwhile for ibuprofen at approximately 222 nanometers. These values are important because they represent the wavelength where the compounds absorb light most strongly. Different maximum absorption values occur due to the difference in molecular structure and chromophoric groups present in each drug compound. The absorbance values recorded at the maximum wavelength were then used to construct the calibration curve. For paracetamol, the calibration curve produced the regression equation, which is y equals to 0.0679x plus 0.0117 with an r-square value of 0.9947. For ibuprofen, the calibration equation obtained was y equals to 0.0458x plus 0.0195 with an r-square value of 0.9921. So basically, the both r-square values are very close to 1, indicating the excellent linearity between absorbance and concentration. Also, they follow the Beer-Lambert law, which states that the absorbance is directly proportional to concentration when the path length and molar absorptivity remain constant. And then, the strong linearity observed suggests that the UV-Vis method provided accurate and reliable quantitative analysis for both pharmaceutical samples. The calibration equation were then applied to determine the concentration of an unknown samples. For paracetamol, the calculated unknown concentration was 5.99 ppm, while for ibuprofen, showed that the unknown concentration of 5.01 ppm. These concentrations were obtained by substituting the absorbance values of the unknown samples into the calibration equations. The calculated values also fell within the linear calibration range, showing that the calibration curves were suitable for quantitative determination.
To conclude everything, the forensic analysis successfully characterized paracetamol and ibuprofen using a combination of quantitative and qualitative techniques, which showed that UV visible spectroscopy and SEM are highly effective techniques for drug identification. UV-Vis analysis obtained showed a strong linear relationship for both drug samples, and the unknown concentrations calculated of 5.99 ppm for paracetamol and 5.01 ppm for ibuprofen based on their respective maximum peak absorption values were determined. The SEM imaging provided distinct morphological profiles showing the sharp-edged fragmented crystal structures of paracetamol with the rough, flaky, agglomerated microcrystals of ibuprofen. In conclusion, these results confirm that integrating both the molecular absorbance data from UV-Vis spectroscopy with surface morphology from SEM provides a robust and reliable methodology for identifying drug evidence in forensic toxicology investigation.